Welcome to the exercises for Chapter 18. This chapter focuses on applications of calculus in statistics. Let's begin in exercise 1 by exploring the relationship between a CDF and a PDF, in particular of a normal distribution or a Gaussian distribution. So what you are going to do is begin by creating a PDF by implementing equation 3 in NumPy. I will scroll up in a moment to remind you of equation 3. And basically, you just want to translate that formula for a Gaussian PDF into NumPy code. And then you can visualize it with matplotlib. You should get a result that looks like this. You can see I'm setting x to go from -4 to +4. And then here's the key part of this exercise. You want to create 3 CDFs from a normal distribution. First, you calculate it as the cumulative sum in NumPy applied to this PDF that you created. So that is one method of creating the CDF. The second method of creating the CDF is to use the SciPy integrate library and pick one of the cumulative functions. So there's cumulative Simpson, there's cumulative trapezoid, and so on. So you can pick one of those functions and again, calculate the empirical or the numerical approximation of the indefinite integral of the PDF, which gives you the CDF. Okay, and then third is to use the scipy.stats module using a CDF method on the normal function, so the Gaussian function. Now that's 3 different CDFs. In theory, they should all be exactly identical to each other. In practice, there will be some really minor differences just due to some like numerical discrepancies and precision errors and so on that you've seen plenty of times before in the book. But you can plot them on top of each other. Certainly visually, they look identical to each other. So here you see the 3 CDFs that we've created all plotted on top of each other. Here you see equation 3. This is the formula for creating a Gaussian PDF. So this is what you want to implement in code. So translate this into NumPy code. Now for convenience, I have just omitted mu from the code, which means I'm implicitly setting it to 0. And I also define sigma as a separate variable, but then I set it to 1, just to make things simple. Of course, you can set these to be whatever values you like. So here is where I create the PDF in NumPy, just literally by translating that formula that I just showed into code. By the way, here would be the place where we could define a shift on the x-axis if we wanted to, if we had some variable called mu. Okay, but I exclude that here. I do have sigma in here, but that's just set to 1. Okay, so here's the 3 methods for creating the CDF as the cumulative sum in NumPy of the PDF. And here we need to multiply by dx because remember, the CDF is defined as the integral of the PDF. So the integral, we have the integrand, which is the PDF, and then we have dx. So if you would leave this out, then that would be like trying to integrate without having the dx at the end. It's just, you get some scaling issues there. Okay, and then here I have the CDF calculated by the cumulative Simpson function in the SciPy integrate library. And you can see I'm calculating this based on the PDF, setting dx, the parameter input into the cumulative Simpson function dx to be the value of dx, that is just the difference between successive x-axis values that I have simulated here. Okay, and then here I'm using stats.norm.cdf. So this will return a cumulative density function for the normal distribution from these x-axis values. Okay, and then we plot all 3. And yeah, there's not so much you could do wrong at this point. The visualization is straightforward. I think the main point of potential confusion here is with the scaling factors, with the dx. So if your plot looks like this, for example, then you can already tell that something is going wrong by looking at the y-axis of the CDF plot. This should go up to a maximum of 1, but it's a little bit higher than 1. It's like orders of magnitude higher than 1. So that would be your tip, that something was wrong with the scaling, and then you just multiply by dx, and everything is gravy. Now, why would which of these methods should you prefer, and why should you prefer any of the methods? Well, this is probably the least preferred method because it is the most vulnerable to precision errors and accumulating precision errors over larger values of x. This one is great, as you know from previous chapters. Now, the thing is, if you are creating a CDF from a mathematical function that is built into the SciPy library, then you should always use this one. This line of code is simple, it's straightforward, it's easy to use, it's highly accurate. You do not need to define the function like this, so you're less likely to make coding errors, and it's just less code overall. That said, you do not always have the luxury of calculating CDFs based on mathematical functions. Sometimes you need to estimate CDFs or approximate CDFs, or I should say calculate empirical CDFs based on data instead of based on mathematical functions. And that is coming up in the next exercise. I concluded the video of exercise 1 with a question of why you would calculate an empirical CDF when you can just generate it from the scipy.stats library. Well, the answer to that comes from exercise 2. So here, the goal is to generate some data based on random numbers. So it's not real data that we are measuring from the world, but just random numbers that is simulating some kind of data that we might get from the real world. And then calculate a CDF empirically based on those data. Okay, so in particular, you want to generate some data with 2,000 data points, so 2,000 samples. 1,000 of those samples are drawn from a logistic PDF, and 1/2 are drawn from a walled PDF. So to access these functions and to generate random data drawn from these distributions, you can use the RVS method in the scipy.stats library, and I'm not telling you exactly how to do that because that's part of the goal of this exercise, to figure that out. But of course, I will show you the solution in the code in a moment. Anyway, so generate your data set of 2,000 sample points, and then you can visualize the data. Let me zoom in a little here, like this. Okay, so you can draw the data like this, visualize the data. Here we have a empirical PDF of the two individual data sets and the full data set, so combined across the two parts of the data set from the two different distributions. And to generate this estimated PDF, I used numpy.histogram. So the function histogram in the numpy library that returns bin edges and y-axis values, so counts, which you can normalize to a probability estimate. And then here in panel C, you can see the estimated CDF based on the PDFs that you see in panel B. Now, these CDFs do not come from a mathematical formula. They are calculated based on data. And again, this is random data that we're actually drawing from mathematical distributions. But you can imagine that these random numbers are corresponding to data that we can measure from the real world, from some process. Here is how I create the data. So I have two variables for data 1 and data 2. This comes from stats dot and then the name of the distribution that you want. So in the previous exercise, we used stats.norm.cdf. Here I'm using .logistics.rvf, and RVF stands for random variates. So random numbers generated from a logistic distribution. And the size, so the number of data points that is in data 1 is n divided by 2, so 1,000. And then same thing for the walled distribution. There is a parameter of the walled distribution. Here I just chose 2. based on explorations that I discussed earlier in the chapter, but this actually doesn't matter. You could pick any value here. And of course, that's the same size. Okay, so then we get our two data sets, and I combine them into one vector to simulate one series, or one sequence of data measured from the world. Here I chose to alternate the two data values from the two different distributions just to make the plot look like the data are mixed. There's no, deep, meaningful calculus theorem that says that we should skip the data points every other, so the even numbers and the odd numbers. Okay, so here's where I plot the data. That is very straightforward. Now we need to show the PDFs, the empirical PDFs and the empirical CDFs for each of the three data sets. So I'm doing that in a for loop where I loop over the three different data sets. So data one, the logistic data set, the walled data set, and the combined data set. I'm using numpy.histogram for the data that's variable d inside this for loop. And in general, when you create a histogram, you have to specify the number of bins to use to bin the data. I have discussed the number of bins very, very briefly in an earlier chapter. If you read a book on statistics or take a course on statistics, you will learn in a lot more detail about the various algorithms used to estimate an appropriate number of bins. But just to keep things simple, for here I'm saying bins equals auto, which means that NumPy is going to calculate an appropriate number of bins. I think it's based on the Friedman-Diaconis rule. But anyway, so here we get two outputs. These are the heights, the y-axes, and we can divide by n to get the PDF, the estimated PDF. And we have to divide by n because the heights, this raw output, is the count of the observations between each of the bin boundaries. So we divide by n to convert from counts into a probability or proportion. Okay, and then these bins are the bin boundaries. So there's n plus 1 boundary values for n boundaries, as you know from segmenting data. And so, yeah, here I'm just averaging them together to get the centers of the bins. Okay, so from here, it's very straightforward. We plot the bin centers by the PDF estimate, which is, the heights divided by the total number of data points. And now here to estimate the CDF, I'm just taking the cumulative sum of the PDF values. As you know from the previous exercise, you can also use SPI.cumulative Simpson or cumulative trapezoid to estimate the CDF. That's fine. In fact, that's probably better. Probably is a little bit more accurate numerically than the NumPy approach, but this is how I coded it. Okay, so then I plot those over here in the third axis. Now, what do we see and what do we make of this result? So first of all, again, the data look like they're all mixed together. That is just a choice I made for visualization. If you did not run this line or code that looks something like this, then you would see that the data from index 0 to 999 have one characteristic, and then the second half of the data look qualitatively different. That doesn't change the PDF or the CDF, though, because the ordinal position of the data point has nothing to do with the distributional characteristics. Now, I guess the main point that I want to stress here is for the estimated CDFs that in general, they all just keep going up. They are monotonically increasing functions because CDFs have to be monotonically increasing because they are the integral of non-negative probability distribution functions. But this black line, the full data set, it doesn't look like a CDF that you've seen before in this chapter that arises from a mathematical function. And of course, that's because this is not a analytic CDF that comes from a formula. It is an estimated or an empirical CDF that comes from data. Here we are with exercise 3 of chapter 18. Earlier in this chapter, I showed you the CDF formula and a CDF graph of a triangular distribution, but I did not show you the PDF corresponding to that triangular CDF. And so the goal of this exercise is to create that PDF of a triangular distribution. And you're going to create this in two ways. So the first way is by directly implementing equation 9. This is the equation for the CDF of a triangular distribution. I'll scroll up to that equation in a moment. So implement that equation in NumPy to generate the CDF, and then you calculate its numerical difference using numpy.diff. And that should give you, according to calculus theory, that should give you the PDF of a triangular distribution. Okay, so that's one approach. The second approach to creating a PDF for the triangular distribution is to use the triang.pdf method, which is in the scipy.stats library. Now, this initially seems like it would be easy and straightforward. It does require less coding, but it's unfortunately not quite so straightforward to use. And that is because the triangular distribution function does not take the three input parameters that are used to characterize a triangular distribution, so A, B, and D. Instead, it takes three different parameters, and you will need to look into the docstring, maybe do some online searching, and do some algebra and figure out a way to translate these three parameters, A, B, and D, into the inputs that triang function takes. Nonetheless, once you figure that out, you should have two versions of the PDF, and in theory, they should be identical to each other. So the next step is to visualize them in a plot that looks like this. So the black line here corresponds to the PDF that comes from directly implementing the formula for the CDF in NumPy, and then differentiating that. And then the diamonds here correspond to the PDF from the scipy.stats library. And I've downsampled those results here just to make it easier to visualize. I think it's every 20th data point I'm actually drawing. And then you can see I'm also drawing some markers here to indicate the locations of the parameters A, B, and D. Here you see equation 9. This is a piecewise function, and it generates the CDF of the triangular distribution. There's 4 pieces for all the numbers less than A, all the numbers greater than D, and those are just equal respectively to 0 and 1. And then for the values between X and B and between B and D, we have a fairly straightforward algebraic expression that shouldn't be too difficult to implement directly in NumPy. Here I'm specifying the 3 parameters of the triangular distribution, A, B, and D. Here I'm specifying the x-axis values. You can see I go from a little bit less than A to a little bit greater than D. And here is the code where I define each of these 4 pieces. So the first piece actually just initializes the entire CDF, and then I'm going to overwrite other numbers on top of this. So it starts off as being all zeros. And then the other 3 pieces have the same format with 2 lines of code, where the first line of code finds all of the x-axis values that correspond to that particular piece. So for example, for piece 2, we want to find all of the x-axis values that are greater than A and less than or equal to B. And then for the CDF, for those x-axis values, we replace that from zeros. They're initially zeros, and they get replaced with these formulas here from the equation I showed in the book. So that's piece 2, piece 3, and piece 4 is also simple to construct. It's just all ones. Okay, now I did not specifically mention in the instructions to visualize the CDF. However, it's always a good idea to visualize the math functions and data sets that you're working with. For example, it would be really easy to make a coding mistake here like this. So here's a coding mistake. Simple, honest mistake. I can make a mistake like this. You can make a mistake like this. Everyone can make a mistake like this. But you look at this and you see it's obviously not a CDF, right? A CDF is a monotonically increasing function. It can never drop down, certainly not down to 0 at any point. This is clearly not something we would want to work with, not to translate into a PDF. But, this was a coding mistake, but it didn't produce any errors or warning messages. So without visualization, it might be difficult to know that we have a mistake. Anyway, now I'm confident that the code is correct. This I will get back to in a moment. Okay, so here is the first method of creating the PDF. That is simply the empirical derivative of the CDF. Okay, very straightforward. As you know from earlier in the book, the output of numpy.diff will have one element less than its input vector. So that's why I am prepending by a 0, just to make the length of PDF be the same as the length of CDF, which is the same as the length of XX. So this is just for, convenience in visualizing and plotting. Okay, so here is the how we create this triangular PDF in SciPy.stats using the PDF method on the triang function. Okay, so we input the x-axis values, and now the three inputs that SciPy wants are loc, c, and scale. Now, loc actually corresponds to point A, so that's pretty easy to specify. Scale, it turns out, is the distance between A and D. So the distance between this point here and this point here is what Python expects for the input to this fourth input argument, scale. Now that is 3. We can just look at this plot and calculate that it's 3 because this is 4 minus 1. So that is how you get this parameter. And this number C here corresponds to this point here, which I labeled B. And you just need to look up the formula in the docstring and then convert that using some algebra. And how do we see that? So we can look up the docstring or the help file for this function by writing out the name of the function or the object and then 2 question marks at the end. And that will give us this help string. You can see it opens up in this little side menu here. Okay, so now we see the triangular distribution can be represented with an upsloping line from loc, so that is parameter A, to loc plus c times scale, so loc plus, and then downsloping from there to loc plus scale. So this is point D. And then this is point B. So you just need to get out a piece of paper and a pen and write down some of these different equations and do some algebraic manipulations. And eventually you will come up with the result that what Python expects for parameter C corresponds to B minus A divided by D minus A. This is basically the proportion across from here to here that you want this point to be. Now, why the SciPy.stats library developers made it this way and not just allowed you to input A, B, and D as every other human being on planet Earth does, I cannot say or justify, but this is how it is. Anyway, you will also remember from earlier in the book that the outputs of these PDF functions are not natively scaled to be valid PDFs. Instead, we need to scale them by dx, and that's why I have this line here. Okay, so that was all the hard part of the exercise. The rest is just plotting. Here I'm plotting the PDF calculated as the derivative of the CDF. Here I'm calculating or plotting the PDF from SciPy.stats, and you can see I'm visualizing only every 20th point. Again, that's purely for visualization. That's just to make the plot a little bit easier to look at. And there you go. Now we have a PDF of a triangular distribution. Here we are with exercise 4 of chapter 18. The goal of this exercise is to calculate a p-value from a z-value using 3 different methods. The first method is the way that you should always do it because it's the best, it's the cleanest, and it's the most accurate. And that is using stats.norm.cdf. The second method and also the third method are interesting to explore from an educational perspective in terms of concepts in calculus, but these are two methods that you should not use when calculating p-values in practice if you're actually doing data science. Okay, the second method is to create a PDF from stats.norm.pdf and use NumPy to sum all of the values that are equal to or to the right of z0, which is 2. So that's the p-value that we want to calculate from the corresponding z value. And the third is the same PDF that you got from stats.norm.pdf, but now instead use spi.trapezoid to calculate the definite integral instead of just summing all the values in NumPy. And you can print all of the results like this. So here is from the CDF. Now your results here for the CDF should match mine exactly. For numpy.sum and numpy.trapezoid, those numbers should be roughly consistent with what you see on the screen here, although they might be different depending on the values of the parameters that you pick when implementing this simulation. I'm going to have quite a bit more to say about this after I show you the Python code. But first, I want to show you figure 12 just as a reminder of what we're doing, what these two different methods, or kind of three, but one is just two different variants of a method. Two different methods of calculating the p-value. So imagine we have a z value of, in this case, it was 2.05, but for this exercise, you're using a value of exactly 2. Now, the p-value is the total area greater than this value in the PDF. So that's the shaded region here that you see. So going from z equals 2 up to z equals infinity, all of that area is what you will, that is the p-value. Okay, but you can also calculate that from the CDF. Okay, so these are the two ways that we are going to calculate the p-value in this exercise. So here, I'm specifying a z value of 2. And here is method 1 directly from the CDF. Now, why do we say 1 minus the CDF? Well, the idea is, let me copy and paste this. What we're really doing here is implementing the fundamental theorem of calculus part 2. So we're really saying that this is infinity. This is not a real Python variable. I'm just writing this out. The theory of calculus plus the theory of statistics and p-values tells us that the p-value is the improper definite integral between 2 and infinity. And then to calculate that, we write the CDF at infinity minus the CDF at 2. But we know that a CDF, or part of the definition, the mathematical definition of a CDF, is that it goes up to 1. It asymptotes up to 1. So the top value is 1 as we approach infinity. So therefore, we just write 1. And that is why this is the correct code to calculate a p-value. Okay, so now to calculate the PDF in order to create to estimate the p-value. So here I'm specifying numbers that go from our z value, which is 2, up to, in this case, I'm choosing 50, right? So here with this code here, I showed you that we're calculating up to infinity, but this is not a value of infinity. This is a value of 50, which is quite a bit smaller than infinity. And I'm going to have more to say about this point after showing you the code. So, or going through the rest of this code. So linearly spaced numbers from 2 up to 50, and then I define the PDF of those z values. Now this is not a full PDF, right? I'm only starting at 2 because that's the value that we care about. And then I sum over all those values and scale by df. Okay, so this should be the area of the PDF from 2, a value of z equals 2, up to infinity. And now here I'm doing the same calculation, but I'm using the trapezoid method in scipy.integration. Okay, so otherwise that's the same. Okay, and then I'm just printing out the result here. Why did I specify or create the PDF only up to 50? So what again, as I mentioned, what we really want to do is calculate the area between z equals 2 and z equals infinity. But you can also see that this normal distribution, this PDF, becomes vanishingly tiny as we get larger and larger values of z, or further away from 0, further away from the origin. So at some point, you get to these very large values, and they're just making such a tiny, tiny contribution to the total area under this curve that we don't really need to calculate this axis all the way out to like 100 bajillion, right? Because the area contribution is so tiny. So I arbitrarily picked 50 as being some number that seems to me relatively large and yet, going to have a vanishingly small contribution. This is exactly why it's better to calculate from the CDF and not from the PDF. So I hope that's clear. These two methods of calculating a p-value are fantastic for right now, for working through an exercise in a textbook on calculus. But when you're doing actual statistics, it's way better and more accurate to use this method based on the fundamental theorem of calculus. Now, what you can try doing is changing the n and changing the top value here to see how that affects the accuracy of these approximations from the PDF to the actual result from the CDF. The goal of exercise 5 is to compare statistical moments that are calculated in two different ways. One way of calculating a statistical moment is analytically by applying the moment generating functions to mathematical PDF functions. And for this way of calculating statistical moments, you don't need a single data point. All you need are math equations. However, not all data come from clearly defined mathematical distributions. So instead, when working with real data, you calculate the statistical moments empirically based on the measured data. And that is the second method of calculating moments that we are going to use in this exercise. Now, we're not actually going to go out into the real world and gather data. Instead, we are going to generate random numbers based on certain distributions. Okay, so let us begin with the normal distribution. So what you want to do is calculate the first 4 moments of the normal or Gaussian distribution based on the SciPy.stats library. So you can do that without a single data point. And then you want to generate 5,000 data points that are randomly drawn from a normal distribution. And again, calculate the first 4 moments empirically based on these 5,000 random data points drawn from the same normal distribution. So the empirical moments and the theoretical analytic moments should line up quite closely, maybe not perfectly because we are working with random numbers, but they should be pretty consistent with each other. Okay, and you can calculate those moments using functions in NumPy and SciPy. For example, the first moment is the mean, and you can simply use numpy.mean to calculate the first moment. Okay, and then, let's see, then you want to make a figure that looks like this. Here we see the analytic PDF and the empirical estimate of the PDF that I calculated with a histogram. So you take a histogram of the data, the 5,000 random data points, normalize both of these PDFs so they have a maximum value of 1, so they're visually comparable. And then you can see below, I have this table printed out with the mean, the variance, the skew, and the kurtosis. So then the top row shows the empirical calculation from the data, and the bottom row shows the analytic calculation from formulas derived from or I got these numbers from the SciPy.stats library. Now, your resulting numbers for the second row should match my results exactly. The results for the top row should be pretty similar, but again, because we are generating random numbers, they won't be exactly identical. Okay, I'm going to switch to code now and show you the code for panel A for the normal distribution. Don't worry yet about panel B. I'm going to get back to that a little bit later. Here I'm generating the analytic PDF, and you can see that I am normalizing it by dividing by its maximum. Now, technically, formally, this is no longer a true PDF because I'm changing the numerical values, but the normalization here, max val normalization, is just used for the visualization for this plot. Okay, and then here I'm generating an empirical PDF. So here I get random variates, you've seen this function before, from a normal distribution and 5,000 points here, according to this sample size. Then I'm getting the histogram of these data, and also then just dividing the histogram counts by the maximum number of counts, which again is exactly the same max val normalization that I'm applying here. Okay, so then plotting those, and let me show you that plot first, and I'll get back and talk about this code. Okay, so here we see the analytic PDF and the empirical PDF. There's basically just 2 points that I would like to make here. One point is that the empirical PDF looks a little bit wobbly, it looks a little bit ugly and rugged compared to the beautiful, pure, smooth analytic PDF. So this empirical PDF is generally a pretty good estimate. It's a pretty good approximation, but obviously it comes from random data. So each time we generate the function, it's, the exact nature of the distribution empirically will look slightly different. Another thing I would like to note is that the analytic PDF has a line going all the way to the edges of the plot, whereas the empirical PDF does not. So this histogram, this estimate of the PDF, only stops, in this case, goes a little bit below -4, and here it's a little bit above 3. Now, why is that the case? Well, in the analytic distribution, there should be data values over here at x equals, 100. So the probability of observing a value of x equals 100 in the normal distribution is really, really, really tiny, but it's non-zero. So we do have a line going all the way out there for the true probability distribution or density. However, in the empirical data, it's just so incredibly unlikely that by chance we're going to randomly draw a number that is equal to 100 that, so we basically never get that far out. So empirically, we're only getting, a subset of the true PDF. Okay, so that said, that's going to be relevant for the next part of the exercise. Here's where I'm calculating the moments. So I'm using stats.norm.stats, so descriptive statistics of the normal distribution, and the moments that I want to get out are inverse. That's just kidding. That's not one word. This is 4 letters corresponding to the mean, the variance, the skew, and the kurtosis. And then here for the moments from the data, I'm just inputting the data into numpy.mean, numpy.var for variance, stats.skew, and stats.kurtosis. So these are the empirical measurements. And yeah, you can see they are slightly different from what I showed in the book figure, but that's totally fine. These are random numbers. They're going to look a bit different every time I run this code. And if you like, you can just, qualitatively, loosely, you can try changing the sample size to see whether that allows these parameters to get closer, these estimates to be closer to their true expected values. Okay, that was for the normal distribution. The next part of this exercise is to repeat exactly the same procedure, but now using a Pareto distribution. So the code that I have here is literally exactly copy pasted from the previous cell. The only changes I made were minor. I replaced norm with Pareto. That's it. And then, I think the title of the panel changed. Otherwise, it's exactly the same code. Okay, let's see what this looks like. So here we see, again, that the empirical and analytic PDFs look pretty similar to each other at like a qualitative sense, but they are distinct. So the analytic PDF in this case happens to go down to smaller numbers with more kind of shifted or scrunched probability. we have values here of 0. Now, in theory, the empirical PDF also has values of 0 here, but they're not being plotted. They're not even being calculated because the histogram function looks for values that are, corresponding to the smallest values in the data set. We can run this again just to see if this lines up. No, it looks like it lines up slightly better, but there's still a little bit of a divergence. Okay, now let's look at the moments for the data, the empirical moments, and the analytic moments. So the mean matches very, very closely within this resolution. Variance matches, that's great. The skew, it's not so close. And here the kurtosis seems to be really off. Now, why is the kurtosis so off here? So it's 5 points of being off here compared to, for the normal distribution, they were much, much closer. Literally orders of magnitude, 3 orders of magnitude closer for the normal distribution compared to the Pareto distribution. Here is the answer. It's not obvious from this plot, but we have to think about the Pareto distribution and the discussion that I had earlier in the text book, earlier in this chapter, about a Pareto distribution. So one of the features about a Pareto distribution is that there are very, very large values. They have low probability, but they are very, very large values. And so when we generate random data with only 5,000 points, we just don't, by chance, we just don't randomly sample enough really, really large values. So they get underrepresented. And that means that the distribution towards the center or towards the left is reasonably accurate, as reflected in the mean and the variance being accurate. But the further we get to the right, the less accurate our empirical estimate is going to be, because we are just not sampling enough from this distribution to get these really, really large values that have a low probability of occurring. And these are in the tails, in particular in one tail. So that skews or, biases the skew and the kurtosis. Just to give this a little bit of real-world context, the Pareto distribution is often used to model wealth. So you have a lot of people with very little wealth, unfortunately, but that's just how it is. And the larger the amount of wealth, the fewer the people who have that amount of wealth. Now, if you would just go walk around in the streets of whatever is your favorite city to visit, pick 500 people, what are the chances that in those 500 people, you would be sampling from the top 0.001% of wealth in that city? It's pretty small. You're not going to just randomly sample Jeff Bezos or someone who is like unbelievably wealthy. And the analytic PDF and the analytic kurtosis actually incorporates those expected data points. But empirically, those expected data points are just really unlikely to occur by chance or by measurement without some very specific methodological intervention. Okay, and to demonstrate this, what I encourage you to do is increase the sample size. So here it's 5,000. You can increase the sample size maybe to 50,000 or 500,000, and you will find that as the sample size increases, the match between the expected and the actual kurtosis is going to increase. So this number is going to get a little bit larger. It will probably never get all the way up to 70.8, but that's okay. It will get a little bit larger. By the way, I just went back to the book real quick, and I saw that the figure in the book shows a kurtosis of 28, whereas the code that I just ran generated a value of 65, so that was much closer. So I just, out of curiosity, ran it again, and now I got a kurtosis value of 38 and a skew that is very close to the expected skew. And basically what happened was when I, happened to run the code while recording, we just happened to randomly sample some very large values. It's unlikely to happen, but it can happen. This is the nature of working with random data. The main question that we will be asking in exercise 6 is, which of these two areas is bigger? In other words, is the definite integral of a PDF from a normal distribution whether that area between z equals 1 and z equals 2 larger or smaller than the area of the same PDF between 2 and plus infinity. Now we can just think about the range or the domain on the x-axis that we're considering here. This is 1 to 2. That's a unit of 1. And here is the distance between 2 and infinity, which is a distance of infinity. It is unbounded growth. It is infinitely larger than the distance between 1 and 2. But the question is, what is the area between the PDF for normal distribution between 1 and 2 versus the area between 2 and infinity? So what I would like you to do is first take a guess, make an intuition. What do you think? Which one of these is bigger, A1 or A2? Just based on looking at this. And then once you have your guess, I want you to actually calculate that in Python. So calculate A1 and A2, and then make a visualization. Now, I'm not going to show you the visualization now to build a little bit of suspense, but it's in the next page in the book, so you can look at it if you want. And of course, I'm going to show the visualization in code and discuss the interpretation and implications. Here are the two z values that we are using. Actually, there's a third one, which is infinity, which is implicitly in here. Okay, so this is I call this P for p-value, but it's the area under the normal distribution between z equals 1 and z equals 2. And how do we calculate that area? Of course, we use the fundamental theorem of calculus part 2. So we get the CDF at that z value, the second z value minus the CDF at the first z value. Okay, and then here, so I've mentioned this a couple of times before, but essentially what we're really doing here theoretically is saying the CDF at infinity minus the CDF at 2. But we know that the CDF at infinity must equal 1, so we can just write 1 minus the CDF of 2. Okay, and now, drum roll please. I assume you're doing a drum roll. Here I have converted this into percent, basically just by multiplying by 100, very straightforward. So we find that the area between 1 and 2 is 13.5%, let's just call it 13%, and between 2 and infinity is 2%. So in fact, the area under the normal distribution between 1 and 2 is 6 times greater than the area between 2 and infinity, even though infinity is an infinite time, infinitely larger than the distance between z equals 1 and z equals 2. Okay, I don't know if you are surprised or not surprised. I cannot see your facial expression. But the answer, the reason why this happens, why this is the result, is that the normal distribution tapers down so quickly to 0 that all of the numbers above, let's say, I don't know, 3, 4, maybe z equals 5, are so vanishingly tiny that they make basically no contribution whatsoever to the resulting area. Now, those are just words. Let's look at a picture so we can see what this really looks like. Okay, so here I create a normal distribution from -4 to +4, and then I'm just making a plot, and then I'm drawing in two areas here corresponding to the area between Z1 and Z2, so 1 and 2, and between 2 and everything bigger than 2. Okay, now when you look at this plot, I think this makes it really clear what is going on here. So this area accounts for 13% of the total area of the curve under this function. And then from 2 to infinity, you can already see it's just a tiny chunk. So the total span on the x-axis is ginormous, but all the values above 3 or 4 are just so small. They just make such infinitesimal contribution that the end result ends up being really small. Exercise 7 of chapter 18 is fun and interesting and open-ended. There's no right or wrong answers. There's no solution in the online code file. There's just interesting functions for you to explore, visualize, and play around with. So here's what I want you to do. Go to this website, and I will show you this in a moment, look for the continuous distributions that are built in to the scipy.stats library, and then copy and modify the code that creates figure 9 to explore what these different distributions look like. So first, let me scroll up to figure 9, and then I'll show you this website. Here is figure 9, and essentially I'm just showing the CDFs and PDFs from one particular distribution. In this case, it's a Laplace distribution with 3 different parameter sets. Okay, now there's nothing special about the Laplace distribution for this particular exercise. This is just to give you a sense of what the figure looks like and which code to modify. So this is for a Laplace PDF and CDF. Also, in this chapter, I introduced you to the normal distribution, the Pareto distribution, the logistic distribution. I forget if I did exponential distribution. There's also the uniform distribution, which I didn't show you, but it's used a lot in applications and in statistics. And now, if you go to this website that I listed, it's the list of functions in scipy.stats. And you can see if you scroll down a little bit, we get to continuous distributions. So this is a long list of all the probability distributions that you can explore in Python. So here we see the Pareto distribution. We've worked with this many times. Lots of interesting distributions. The T distribution, we worked with the triangular distribution. There's lots of distributions here. So your mission for this exercise, should you choose to accept it, is just to pick a couple of these ones, like what is this? NCT, okay, non-central students T continuous random. Just pick a couple of these distributions. Maybe this one looks interesting, Nakagami, and copy paste the code that generates figure 9, change some of the variables, and have fun.